Hello and welcome back, deep divers. We've all dreamed about a true quantum internet, or being able to teleport information instantly and securely across the entire globe. Well, for decades, one massive roadblock has kept those sci-fi ideas from becoming our reality. Today, we're going to unpack the breakthrough that finally smashed it to pieces.
But before we get into the solution, let me ask you this. What do you think is the single biggest thing holding back technologies like quantum teleportation? It's a puzzle that, and I'm not kidding, for over 25 years has been this massive bottleneck for any real progress. In this deep dive, we're going to see how scientists finally cracked the code.
Welcome to the Deep Dive Classroom. All right, here's our lesson plan for today. First, we'll lay out the core problem. Then you'll meet the quantum hero of our story. It's called the W state. After that, we'll tackle the measurement that seemed absolutely impossible, reveal the honestly beautiful solution, and finally explore the incredible future this all unlocks. So, maybe grab a notebook, get ready to think like a physicist, and let's jump right in.
Okay, let's get into the problem. We've all heard the amazing promises of quantum tech, right? Unhackable communication, computers with almost unimaginable power. But for the longest time, a really fundamental hurdle has kept all of these breakthroughs stuck in the lab. See, the challenge wasn't just creating these special quantum states, but being able to reliably measure them, to even know if you'd made them correctly.
Now, every great story needs a hero. And in this one, our hero is a very special kind of quantum entanglement called the W state. It has this unique superpower that makes it pretty much perfect for building real-world quantum systems. But it also came with this hidden, fatal flaw that made it almost impossible to actually work with. So what even is a W state? Well, to put it simply, it's a way of linking the fates of multiple quantum particles, like tiny photons of light. They become this single, interconnected system, and it doesn't matter how far apart they are. But here's the thing you have to remember: not all entanglement is created equal.
And this right here, this brings us to the W state's superpower. It's resilience. See, most other forms of entanglement are like a super delicate chain made of glass. If you lose just one particle, poof, the entire connection shatters. The W state, though, it's more like a spider's web. You can snip one of the strands, but the rest of the web stays strong. And that toughness is exactly what you need for a real-world quantum network, because let's be real, losing a particle is going to happen.
So you're probably thinking, if the W state is so great, why weren't we using it for everything? Well, that brings us to the central conflict of our story. Identifying, or just measuring, this incredibly useful state was a monstrously difficult task. It was like an impossible puzzle.
For years, the only tool scientists had in their toolbox was this thing called quantum tomography. You can kind of think of it like a medical CT scan, but for a quantum state. The problem is, for this very specific task, it was just an incredibly clunky and inefficient tool. It required a massive, and I mean massive, number of repeated scans just to build a blurry picture of what was even going on. Trying to use quantum tomography for this was like, imagine trying to solve a million-piece jigsaw puzzle, but you're in the dark. You can only feel one piece at a time, and you have absolutely no idea what the final picture is supposed to look like. You just have to repeat the process thousands upon thousands of times just to get a rough idea of the full image. And here's the real killer. As you add more and more particles to your W state, which you need to do to build a bigger network, the number of measurements you have to take grows exponentially. It just explodes. It very quickly becomes not just impractical, but physically impossible. This was the bottleneck.
But then came the aha moment. A team of brilliant researchers in Japan decided to just stop trying to brute force the problem. Instead, they started looking for a shortcut, a hidden pattern, something that could change everything.
And they found it. The answer was in a property called cyclic shift symmetry. What they realized was that if you rotate the positions of the photons inside a W state, the overall state doesn't actually change. It's kind of like a familiar song, right? You don't need to hear every single note in perfect order to recognize the melody. So they built a special optical device that could just listen for this specific melody, allowing them to identify the W state instantly in one shot.
To really understand the impact here, just listen to these words from the lead researcher, Shigeki Takeuchi. He said, "More than 25 years after the initial proposal, we have finally obtained the measurement for the W state." Just think about that. A quarter-century-old problem, a problem that stumped so many people, solved.
So the bottleneck is gone.
the puzzle is solved, but what does this actually mean for the future? What new doors has this breakthrough really opened up for all of us?
Well, this new technique basically makes everything that relies on the super resilient W state suddenly practical. We're talking about quantum teleportation that's way more robust and less prone to errors. We're talking about quantum communication that's much more secure against information loss. And maybe the most exciting thing, it unlocks distributed quantum computing and truly scalable quantum networks, where many quantum systems can be linked together to create something far, far more powerful than the sum of its parts.
So what's the key lesson from today's class? What's the big takeaway? I think it's that sometimes the most complex problems don't need more brute force, they need a different perspective. By finding a hidden pattern, a little bit of symmetry, these scientists turned an impossibly slow, frustrating measurement into a single elegant step. It's such a powerful reminder that a clever insight can be so much more powerful than brute force. And that leaves us with a final question for you to think about. With this massive barrier now gone, which of these quantum technologies do you think will be the first one to really change our daily lives? Let me know what you think down in the comments below. And hey, if you found this lesson helpful, hitting that like and subscribe button really does help us reach more learners just like you. And while you're at it, check out our new merch. Your support is seriously what keeps the Deep Dive Classroom open. Thanks so much for joining the class today, and I'll see you for our next Deep Dive.